Hello everyone. We're going to be looking at a few more integrals that can be done using partial fractions today. I will provide you with a tidy summary of what you can do if the degree of the denominator is larger than the numerator after this first example. Following that, we will look at what to do if the degree of the denominator is less than or equal to the degree of the numerator. And finally, I'll leave you with a couple you can try out on your own. So in this first example, there is an unfactorable quadratic factor in the denominator. We can start by factoring a 3 out of the numerator in this integral, leaving us with x squared plus 5. And we can factor a 2 out of the denominator, leaving us with x cubed plus 3x. And now we're going to try to write this term as a sum of simpler fractions. So we have x squared plus 5 up top, and x times x squared plus 3 on the bottom. Notice we have a nonlinear term appear in the denominator. If this happens, it might be possible to write this in the following way. So for this question, we're going to have a over x plus bx plus c over x squared plus 3. Next, we're going to multiply both sides of this equation by x times x squared plus 3. So on the left side of the equation, we're left with x squared plus 5. And on the right side of the equation, we have a times x squared plus 3 plus bx plus c times x. So now we have x squared plus 5 equals ax squared plus 3a plus bx squared plus cx. And we can group the x squared terms. So we have a plus b times x squared. And the only x term would be cx. And then we have a plus 3a. So we require a plus b to equal 1. C needs to be 0. And 3a needs to equal 5. So given that 3a equals 5, we know that a equals 5/3. And given that a plus b needs to equal 1, and we already know that a is 5/3, we can solve for b. So b is equal to 3/3 minus 5/3, or in other words, b equals negative 2/3. So now we can write x squared plus 5 divided by x times x squared plus 3 as a over x, and we determined a was 5/3, so we have 5 over 3x, and then we have bx plus c divided by x squared plus 3. So we determined b was negative 2/3, c was 0, and that's over x squared plus 3. And remember, we also had a factor of 3/2 out front, so we multiply both sides of this equation by 3/2. We can determine a new expression for our original integral. So if we distribute 3/2 into this first term, we end up with 5 over 2x. And when we distribute 3/2 into this second term, we end up with negative x over x squared plus 3. So that means we can write our original integral as 5/2 integral 1 over x dx minus the integral of x over x squared plus 3 dx. So this one's easy enough. That would be 5/2 ln x. And we can do the second one using substitution. So if we let u equals x squared plus 3, then du equals 2x dx, which means x dx is equal to du over 2. And we can see an x dx appear in this integral, and x squared plus 3 in the denominator. So that would make this second integral be negative 1/2 du over u. So next we would have 5/2 ln x minus 1/2 ln u, and ln of u would be equivalent to ln of x squared plus 3. So ln x squared plus 3 plus the integration constant. So here's what to do in general if the degree of the denominator is greater than the degree of the numerator. We covered this first type in example number 1, where the factors in the denominator were x and x minus 5. We covered the second type in example number 2, where the factors in the denominator were x and x minus 1 squared. And we just covered this third type in example number 3. So what do we do if the degree of the denominator is less than or equal to the degree of the numerator? That's exactly what's happening with example number 4. In this situation, we need to perform a long division. So we're going to go x plus 2 into x minus 4. So if we focus on the first terms, x and x, x fits into x once, and then we need to multiply 1 by each of these terms and subtract it from the dividend. So we subtract x plus 2 from x minus 4. X minus x is 0, and negative 4 subtract positive 2 is negative 6. So we have a quotient of 1 and a remainder of 6. And with the result of this long division, we're going to try to write our original integral as a sum of simpler fractions. In order to do that, we're going to use this idea, which is true in general. So we have the dividend equals the divisor times the quotient plus the remainder. So more specifically in this example, we have x minus 4 equals x plus 2 times 1 minus 6. And if you do a quick simplification of the right-hand side of this equation, you'll see that that's true. If we want to come up with an expression for x minus 4 divided by x plus 2, we just need to divide both sides of this equation by x plus 2. So that gives us x minus 4 divided by x plus 2 equals 1 minus 6 over x plus 2. And our original integral becomes a lot simpler in this form. So the original integral is equivalent to the following expression. This first one is quite simple to do. It'd just be x, and this one here would be ln of x plus 2. So we have subtract 6 ln of x plus 2 plus c. In example number 5, if you would prefer to factor the bottom of this and set up a synthetic division, I'm sorry to report that this doesn't seem to fit the mold. Neither x plus 2 nor x minus 1 are factors of the quartic function in the numerator. Thankfully, there's an easier way to proceed. We'll still end up doing long division, but it's a lot simpler than it looks. So x squared plus x minus 2 is our divisor, and 3x to the 4th plus 3x cubed minus 5x squared plus x minus 1 is our dividend. So if we focus on our first terms, x squared and 3x to the 4th, I would need to multiply x squared by 3x squared to get 3x to the 4th. So next we multiply 3x squared by the divisor and subtract that from the dividend. So 3x squared times x squared gives us 3x to the 4th, and 3x squared times x gives us 3x cubed, and 3x squared times negative 2 is negative 6x squared. Now 3x to the 4th minus itself is 0, 3x cubed minus itself is also 0, and negative 5x squared plus 6x squared is x squared. And next we drop these terms. Now we focus on x squared and x squared. So x squared needs to be multiplied by 1 to give us x squared. Now we multiply 1 by the divisor and subtract that. So we would have 1 times x squared, which is x squared, 1 times positive x, which is positive x, and 1 times negative 2, which is negative 2. So x squared minus itself is 0, x minus itself is also 0, and negative 1 plus 2 is 1. Next we can write the dividend is equal to the divisor times the quotient plus the remainder. So 3x to the 4th plus 3x cubed minus 5x squared plus x minus 1 is equal to x squared plus x minus 2 times 3x squared plus 1 plus 1. We can now divide the left and right hand side of this equation by x squared plus x minus 2. These terms will disappear, and now we can write the original integral as the integral of 3x squared plus 1 dx plus the integral of 1 over x squared plus x minus 2 dx. This integral is fairly straightforward, but it looks like we're going to have to do the partial fraction treatment on this one again. So if we factor the bottom, we get the integral of 1 over x plus 2 times x minus 1 dx. And we can express this as the sum of two simpler fractions. So 1 over x plus 2 times x minus 1 can be written as a over x plus 2 plus b over x minus 1. If we multiply both sides of this equation by x plus 2 and x minus 1, we get 1 equals a times x minus 1 plus b times x plus 2. Now if x equals 1, the equation above gives us 1 equals a times 1 minus 1, which is 0, plus b times 1 plus 2, which is 3, so 3b. So therefore b is equal to 1/3. Now if x equals minus 2, the equation above gives us 1 equals negative 3a plus 0. So therefore a is equal to negative 1/3. Now we can proceed with this integration. So we have the integral of 3x squared plus 1, which would give us 3 times x cubed over 3 plus x. And the second integral can be written as negative 1/3, 1 over x plus 2 dx, plus 1/3 integral of 1 over x minus 1 dx. So in the end we would get x cubed plus x minus 1/3 ln x plus 2 plus 1/3 ln x minus 1 plus the integration constant. If you're looking for a challenge, you can try this example out on your own. I'll leave it to you to show that this is the result. If you start this integral with the following substitution, it's a lot more manageable. So that's it for me for today. I'll get you to try these questions out on your own, and I'll see you next time.